Right now, light is hitting your eyes. It's the most ordinary thing imaginable. You flick a switch and a room fills with it. You step outside and the sun pours it over everything. Light is so familiar that most people never stop to ask what it actually is. And that's where things get strange. Because light is not a substance. It's not a stream of tiny glowing particles flying through the air. It's not a ripple moving through some invisible medium. It doesn't behave like anything else in the known universe. It has no mass, yet it carries energy. It has no size, yet it can spread across billions of light years. It always moves at exactly the same speed, no matter what. And when physicists finally understood what light really is, the answer turned out to be far stranger than anyone imagined. If you find this kind of deep exploration interesting, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you've done 1,000 times. You walk into a dark room, you flip a switch, and instantly the room fills with light. It's so routine, so automatic, that you don't even think about it. Light is just there. It's always been there. The sun provides it during the day. Light bulbs provide it at night. Candles, fires, phone screens, stars scattered across the darkness. Light is everywhere. It's so ordinary that asking what light actually is feels almost silly. Like asking what water is or what air is. You know what light is. It's the stuff that lets you see. But here's the thing, for thousands of years nobody could answer that question properly. What is light? What is it made of? How does it travel from a candle flame to your eye? Is it a substance that flows through the room like smoke or mist? Is it something the candle shoots outward, like tiny invisible bullets? Is it a vibration of some kind, a disturbance rippling through space the way sound ripples through air? Or is it something else entirely, something that doesn't fit into any familiar category? These aren't trivial questions. They tormented some of the greatest minds in human history for centuries. And the answers, when they finally came, didn't just explain light. They reshaped our entire understanding of the physical universe. They revealed connections between phenomena nobody thought were related. They shattered assumptions we'd held since ancient times. And ultimately, they forced us to accept that reality at its deepest level is far stranger than our everyday experience suggests. Let's go back to the 1600s. Isaac Newton, one of the most brilliant humans who ever lived, had a theory about light. Newton believed light was made of tiny particles. He called them corpuscles, from the Latin word for small body. In Newton's picture, when a candle burns, it shoots out streams of these tiny corpuscles in all directions. The corpuscles travel in straight lines through empty space, bounce off surfaces, enter your eye, and produce the sensation of vision. This made intuitive sense. Light appears to travel in straight lines. You can see this clearly when sunlight streams through a gap in the curtains and illuminates dust particles floating in the air. You see a sharp beam, a straight ray, cutting through the darkness of the room. Shadows have sharp edges. Light doesn't seem to bend around corners the way sound does. You can hear someone talking from around a corner, but you can't see them. All of this seemed to support the idea that light is made of particles traveling in straight lines, like microscopic projectiles fired from every light source. Newton was enormously influential. He had discovered the law of universal gravitation, invented calculus, and explained the motions of the planets. When Newton said light was made of particles, most scientists accepted it. For over a century, the corpuscle theory dominated scientific thinking about light. But there was a competing idea. Around the same time Newton was developing his particle theory, A Dutch physicist named Christian Huygens proposed something completely different. Huygens argued that light was not a stream of particles at all. He believed light was a wave, not a collection of tiny objects flying through space, but a disturbance, a ripple propagating outward from its source, much like the ripples that spread across a pond when you toss a stone into the water. Huygens's wave theory could explain certain phenomena that Newton's corpuscles struggled with. It explained why light can spread out slightly after passing through a very narrow opening, a phenomenon called diffraction. Particles travelling in straight lines shouldn't spread out after passing through a slit. They should continue forward in a narrow beam. But waves naturally spread outward when they pass through an opening. You can see this with water waves passing through a gap in a sea wall. The wave doesn't continue as a narrow stream. It fans out in a semicircle on the other side. Huygens's theory also explained why two beams of light crossing each other don't collide or deflect one another. If light were made of particles, you'd expect occasional collisions when two beams meet. But waves pass through each other effortlessly. When two ripples meet on a pond surface, they overlap, they combine for a moment, and then they continue on their separate ways as if nothing happened. Light behaves exactly like this. Two beams can cross through each other without affecting each other at all. But Huygens's theory couldn't explain the sharp edges of shadows quite as neatly as Newton's particles could. And Newton was Newton. His authority carried enormous weight. So for most of the 1700s, science sided with Newton. Light was particles. The matter seemed settled. Then, in 1801, a British scientist named Thomas Young performed one of the most beautiful and important experiments in the history of physics. Young's experiment was elegantly simple. He took a beam of light and shone it at a barrier with two narrow slits cut side by side, close together. On the other side of the barrier, he placed a screen to catch whatever light came through. If light were made of tiny particles, as Newton claimed, you'd expect to see two bright bands on the screen, one behind each slit. The particles would fly through each slit in a straight line and hit the screen in two distinct patches, like two streams of sand falling through two holes. But that's not what Young saw. Instead, the screen showed something completely unexpected. A series of alternating bright and dark bands stretched across the screen. Bright, dark, bright, dark, bright, dark. Not two bands, many bands. A pattern of stripes that extended far beyond the edges of the two slits. This pattern is called an interference pattern, and it's something only waves can produce. Here's why. When waves pass through two slits, they spread out from each slit and overlap on the other side. At certain points on the screen, the peak of a wave from one slit arrives at the same time as the peak of a wave from the other slit. The two peaks add together, creating a wave with double the height, double the intensity. This produces a bright band. At other points, the peak of a wave from one slit arrives at the same time as the trough of a wave from the other slit. Peak meets trough. The two waves cancel each other out perfectly. The result is darkness. No light at all. This alternating pattern of reinforcement and cancellation is the unmistakable signature of wave behavior. Particles cannot do this. Particles don't cancel each other out. Two bullets hitting the same spot don't produce zero damage. Two streams of sand pouring onto the same point don't create emptiness. Only waves interfere destructively. Only waves can produce darkness from the combination of two sources of light. Young's experiment was devastating for the particle theory of light. It demonstrated with elegant and undeniable simplicity that light behaves like a wave. The scientific community gradually accepted the result. By the mid-1800s, the wave theory of light was firmly established. Newton's corpuscles were abandoned. But this created a problem, a deep problem. If light is a wave, what is it a wave in? Every wave scientists had ever encountered was a disturbance in some physical medium. Sound is a wave in air. The air molecules compress and expand in rhythmic patterns, and this disturbance propagates outward from the source. Ocean waves are waves in water. The surface of the water rises and falls, and this pattern of motion travels across the surface. Waves on a guitar string are vibrations of the string itself. The string moves up and down, and this disturbance travels along the string's length. In every case, there's always something doing the waving, something physical, something material. You can't have a water wave without water. You can't have a sound wave in a vacuum because there's no air to vibrate. Remove the medium, and the wave ceases to exist. So what medium carried light waves? Light travels from the Sun to the Earth across roughly 93 million miles of essentially empty space. There's no air out there. There's no water. There's no material of any kind. It's a vacuum, as close to empty as nature allows. Yet light makes the journey effortlessly in about 8 minutes and 20 seconds. What was vibrating? What was oscillating? What substance carried the wave from the Sun all the way to Earth? Scientists proposed a solution. They hypothesized that all of space was filled with an invisible, weightless, perfectly transparent substance they called the luminiferous ether. Luminiferous means light-bearing. This ether supposedly permeated everything, every corner of space, every gap between the stars, even the interiors of solid objects. It had to be incredibly stiff to transmit light waves at such enormous speeds, because waves travel faster in stiffer materials. Yet it also had to be completely undetectable by any means other than light. You couldn't see the ether, touch it, weigh it, or interact with it in any measurable way. Its only role was to carry light. This was already suspicious. A substance that supposedly fills all of space, but can never be detected except through the very phenomenon it was invented to explain, sounds less like a scientific discovery and more like a convenient fiction. But for decades, the ether was taken seriously. It seemed logically necessary. Waves need a medium. Light is a wave. Therefore, there must be a medium for light. The reasoning seemed airtight. Meanwhile, something revolutionary was happening in the world of electricity and magnetism. And this is where the story of light takes its most dramatic and unexpected turn. Throughout the early and mid-1800s, scientists had been making steady progress understanding electric and magnetic phenomena. They knew that electric charges create electric fields in the space around them. They knew that magnets create magnetic fields. They knew that moving electric charges, meaning electric currents, produce magnetic fields. And they knew that changing magnetic fields can induce electric currents in nearby conductors. These were experimental facts, painstakingly established through decades of careful laboratory work by scientists like Michael Faraday in England and others across Europe. Each fact was interesting on its own, but nobody had yet seen the full picture, the way all these pieces fit together. Then a Scottish physicist named James Clerk Maxwell saw something nobody else had seen. In the 1860s, Maxwell sat down and wrote a set of equations that unified everything known about electricity and magnetism into one elegant mathematical framework. There are 4 of these equations, and they are, without exaggeration, among the most important equations in the entire history of science. They describe how electric charges create electric fields, how magnetic fields are generated by currents and changing electric fields, how changing magnetic fields create electric fields, and the fact that there are no isolated magnetic charges. 4 equations, 4 statements about the behavior of electric and magnetic fields. Together, they describe all of classical electromagnetism. And what these equations revealed was astonishing. A changing electric field doesn't just sit there, it creates a magnetic field. And a changing magnetic field doesn't just sit there either, it creates an electric field. These two processes feed into each other in a continuous loop. If you disturb an electric field, the disturbance creates a changing magnetic field. That changing magnetic field creates yet another changing electric field. That new changing electric field creates yet another changing magnetic field. Back and forth, continuously, the two fields generating each other in a self-sustaining oscillation that moves through space without needing any material substance to carry it. Maxwell realized that this self-sustaining disturbance, this coupled dance of electric and magnetic fields, would propagate through space as a wave, an electromagnetic wave. In this wave, the electric field oscillates in one direction, the magnetic field oscillates perpendicular to it, and the whole disturbance travels forward, perpendicular to both fields, at a speed that Maxwell could calculate directly from the known constants of electric and magnetic interactions. He didn't need to measure the speed of the wave. He could derive it from first principles, from the measured strengths of how electric charges push and pull on each other, and how magnetic forces behave. When Maxwell plugged in the numbers, the answer came out to approximately 300,000 kilometers per second, about 186,000 miles per second. Maxwell immediately recognized this number. It was the measured speed of light. This wasn't a rough match. It wasn't merely in the right ballpark. It was the speed of light, precisely, within the accuracy of the measurements available at the time. Maxwell wrote, with remarkable restraint, given the sheer magnitude of what he had just uncovered, that the agreement of these results seemed to show that light and electromagnetism are aspects of the same substance, and that light is an electromagnetic disturbance propagated through space according to electromagnetic laws. Think about what had just happened. Think about the scale of this discovery. For centuries, electricity, magnetism, and light were considered three entirely separate phenomena. Electricity was the stuff of lightning bolts and static shocks. Magnetism was the stuff of compass needles and lodestones. Light was the stuff of candles, sunshine, and starlight. They seemed to have nothing to do with each other. Nobody suspected any connection. Maxwell showed they were all the same thing. Light is an electromagnetic wave, a self-sustaining oscillation of electric and magnetic fields propagating through space at a speed determined by the fundamental properties of those very fields. Light isn't a substance flowing through a room. It isn't a vibration of some invisible ether. It's a traveling pattern in the electromagnetic field itself. The electric field rises and falls. The magnetic field rises and falls in lockstep, perpendicular to the electric field. And the whole pattern sweeps forward through space at 300,000 kilometers per second. This was one of the greatest unifications in the history of science. Three apparently unrelated phenomena revealed to be different facets of a single underlying reality. And Maxwell's equations predicted something else, something with enormous consequences. If light is an electromagnetic wave, then there should exist other electromagnetic waves with different wavelengths and different frequencies. Visible light, the light your eyes can see, occupies only a tiny sliver of what should be a vastly wider electromagnetic spectrum. There should be electromagnetic waves with wavelengths far longer than visible light, and waves with wavelengths far shorter. They would all be the same fundamental phenomenon, coupled oscillations of electric and magnetic fields propagating at the speed of light. The only difference between them would be how rapidly they oscillate. In 1887, a German physicist named Heinrich Hertz confirmed this prediction in his laboratory. Hertz built electrical apparatus that generated electromagnetic waves with wavelengths measured in meters, far longer than any visible light. He detected these waves across the room using a separate receiver. They reflected off metal surfaces. They could be focused by curved reflectors. They traveled at the speed of light. They obeyed Maxwell's equations exactly. They were electromagnetic radiation, identical in nature to visible light, just oscillating at a much lower frequency. These were radio waves. Maxwell had predicted their existence from pure mathematics, and Hertz proved they were real. This confirmed the electromagnetic spectrum, one of the most important concepts in all of physics. At one end are radio waves, with the longest wavelengths, stretching from millimeters to hundreds of meters or more. These carry radio broadcasts, television signals, and phone transmissions. Radio waves pass through your body constantly. You can't feel them, you can't see them, but they're everywhere around you right now. Next come microwaves, with wavelengths measured in centimeters. Your microwave oven uses these to heat food by forcing water molecules to rotate rapidly in the oscillating electric field, generating heat through molecular friction. Microwaves are also used in radar and communications. Then infrared radiation. You experience this as radiant heat. When you feel warmth coming from a campfire or a hot stove without touching it, you're feeling infrared radiation striking your skin. Every object above absolute zero emits some amount of infrared. Your own body radiates it constantly. Night vision devices work by detecting this infrared emission from people and animals. Then comes the narrow band of visible light. This is the specific range of electromagnetic radiation that human eyes happen to be sensitive to. It spans wavelengths from about 400 nanometers, which your brain interprets as violet, to about 700 nanometers, which appears red. In between lie blue, green, yellow, and orange. These are the colors of the rainbow. And the entire rainbow, every color you've ever seen, occupies a remarkably tiny fraction of the electromagnetic spectrum. If the full spectrum was stretched out to the width of the continental United States, visible light would be a strip about the width of your hand. Beyond violet lies ultraviolet radiation, with shorter wavelengths and higher frequencies. The sun emits significant ultraviolet. It's what causes sunburn and can damage skin cells over time. Some insects, particularly bees, can see ultraviolet light. Flowers that appear plain white to human eyes have vivid ultraviolet patterns visible to bees, guiding them toward nectar. Then X-rays, with even shorter wavelengths. These penetrate soft tissue but are absorbed by denser structures like bone, which is why they're invaluable in medical imaging. X-rays from the sun and distant cosmic sources are blocked by Earth's atmosphere, which is fortunate because extended exposure damages living cells. At the far extreme lie gamma rays. These have the shortest wavelengths and the highest frequencies of any electromagnetic radiation. They are produced in nuclear reactions, radioactive decay, and some of the most violent events in the cosmos. They carry tremendous energy and are extremely dangerous to biological tissue. And here is the critical point, the thing that matters most. All of these, every single one, radio waves, microwaves, infrared, visible light, ultraviolet, X-rays, gamma rays, are the same fundamental phenomenon. They are all electromagnetic radiation. They are all oscillating electric and magnetic fields propagating through space at the speed of light. The only difference between a radio wave and a gamma ray is wavelength and frequency. A radio wave oscillates slowly, maybe a few million times per second. A gamma ray oscillates incomprehensibly fast, trillions of times per second. But they are the same kind of thing. Visible light isn't special in any physical sense. It's just the narrow band of electromagnetic radiation that evolution happened to make our eyes sensitive to, because it's the range the sun emits most strongly and that passes through our atmosphere most easily. We call that band light, but it's a tiny window onto a vast electromagnetic landscape. Now, back to the ether. Maxwell's discovery that light is an electromagnetic wave didn't immediately kill the ether idea. Many physicists still assumed the ether existed and that electromagnetic waves were somehow vibrations of this substance. But the ether was about to face its final test. If the Earth moves through the ether as it orbits the Sun, then the speed of light should be slightly different depending on the direction you measure it. Light travelling in the same direction as Earth's motion through the ether should effectively be a bit slower relative to Earth, because Earth is chasing the wave. Light travelling in the opposite direction should be a bit faster, because the wave is rushing toward Earth. It's like swimming in a river. Swim downstream and the current helps you. Swim upstream and the current works against you. The difference would be small, because the speed of light is enormous and Earth's orbital speed is comparatively modest, about 30 kilometers per second. But the difference should be measurable with sufficiently precise instruments. In 1887, two American scientists, Albert Michelson and Edward Morley, built exactly such an instrument. Their interferometer split a beam of light into two beams travelling in perpendicular directions. The beams reflected off mirrors at equal distances and returned to the starting point, where they were recombined. If the speed of light differed between the two directions, the beams would arrive slightly out of sync, producing a visible shift in the interference pattern. The device was exquisitely sensitive. It could detect speed differences far smaller than what the ether theory predicted. Michelson had designed it specifically to settle the ether question once and for all. The result stunned the scientific world. There was no difference. None. Zero. Light travelled at exactly the same speed in every direction, regardless of how Earth was moving through space. The experiment was repeated numerous times over the following years, in different seasons, as Earth moved in different directions around the Sun, with progressively greater precision. The answer was always the same. The speed of light was constant. It did not depend on the observer's motion. This was a crisis for the ether theory. If the ether existed, the experiment should have detected Earth ploughing through it. It didn't. The most straightforward conclusion was that the ether simply didn't exist. Light doesn't need a medium to travel through. Electromagnetic waves are not vibrations of some invisible substance. They are self-sustaining oscillations of electric and magnetic fields that propagate through completely empty space, through pure vacuum, through absolute nothingness. This makes electromagnetic waves fundamentally different from every other type of wave humans had ever encountered. Sound cannot travel through a vacuum. Water waves cannot exist without water. But light needs nothing. The electromagnetic field carries itself. The constant speed of light wasn't just a curious experimental result. It became one of the cornerstones of modern physics. In 1905, Albert Einstein published his theory of special relativity. He built the entire theory on two foundational principles. The first was that the laws of physics are the same for all observers moving at constant velocity. The second was that the speed of light in a vacuum is the same for all observers, regardless of how those observers are moving, and regardless of how the source of light is moving. This second principle sounds simple, almost innocent, but its consequences are among the strangest and most profound in all of science. If light always travels at the same speed no matter what, then our intuitive ideas about space and time must be wrong. Space and time themselves must flex and adjust to keep the speed of light constant. Lengths contract in the direction of motion. Clocks run slower for objects moving at high speeds. Events that happen simultaneously for one observer occur at different times for a different observer. The very fabric of space and time warps and bends to preserve one absolute unchanging fact: the constancy of the speed of light. And that speed was never put in by hand. It was never a measured number that Einstein inserted into his theory. It falls directly and inevitably out of Maxwell's equations. Maxwell wasn't trying to discover a cosmic speed limit. He was just trying to describe how electric and magnetic fields interact. But the mathematics led him, inescapably, to a universal constant: 300,000 kilometers per second. Every second, in every direction, in every reference frame, under every condition. The speed of light is not just a property of light, it's a structural feature of space-time itself. Let's take a moment now to appreciate the wave properties of light, because the wave description is extraordinarily powerful and explains an enormous range of everyday phenomena. Every electromagnetic wave has two fundamental properties: wavelength and frequency. Wavelength is the distance between two consecutive peaks of the wave. Frequency is how many complete oscillations occur every second. These two properties are locked together by a simple relationship. If you multiply the wavelength by the frequency, you always get the speed of the wave. For electromagnetic radiation, that speed is always the same: 300,000 kilometers per second. So, if the wavelength is long, the frequency must be low. If the wavelength is short, the frequency must be high. A radio wave with a wavelength of 1 meter oscillates roughly 300 million times per second. Visible red light with a wavelength of about 700 nanometers oscillates roughly 430 trillion times per second. Gamma rays oscillate at frequencies exceeding 10 million trillion times per second, all traveling at the same speed, always. Light also has a property called polarization. In an electromagnetic wave, the electric field oscillates in a specific direction, perpendicular to the wave's direction of travel. If the electric field oscillates up and down, we call the light vertically polarized. If it oscillates side to side, it's horizontally polarized. Unpolarized light, like sunlight, is a mixture of all possible polarization directions. Polarizing sunglasses work by allowing through only light polarized in one orientation and blocking the rest. This reduces glare because light reflected off flat horizontal surfaces like water or road surfaces tends to be horizontally polarized. Block that polarization and you block the glare. The wave description explains reflection. When an electromagnetic wave strikes a surface, the oscillating electric field pushes and pulls on the charged particles in the surface material, and those accelerating charges re-emit waves that travel back outward. It explains refraction, the bending of light as it passes from one material into another, like from air into glass or from air into water. It explains diffraction, the subtle spreading of light as it passes through narrow openings or around sharp edges. It explains why soap bubbles and oil films shimmer with brilliant colors through interference between waves reflected off the front and back surfaces of the thin film. All of this from a single set of equations, Maxwell's equations. The electromagnetic wave theory of light was spectacularly successful. It unified electricity, magnetism, and optics into one coherent framework. It predicted the existence of electromagnetic waves beyond visible light, and those predictions were confirmed experimentally just 8 years after Maxwell's death. It explained reflection, refraction, diffraction, interference, and polarization, all from 4 equations. By the late 1800s, physicists believed the question of what light is had been answered. Light is an electromagnetic wave, a coupled oscillation of electric and magnetic fields propagating through space at a fixed and universal speed. Except the story wasn't over, not even close, because in the closing years of the 1800s and the opening years of the 1900s, physicists began running into problems. Small problems at first. Subtle disagreements between what the wave theory predicted and what experiments actually showed. Situations where the smooth, continuous wave picture of light didn't match what was happening in the laboratory. These seemed like minor technical issues at first, loose ends, wrinkles that would be ironed out with a bit more work. But they weren't minor. They were cracks in the foundation of classical physics itself, and those cracks would soon split open and give birth to something entirely new. A theory so strange, so counterintuitive, so fundamentally different from anything that had come before, that even the scientists who invented it struggled to accept what it was telling them about the nature of reality. The wave description of light is powerful, and it is correct in many situations. But it is not the whole truth. Light does things that no classical wave can explain. It interacts with matter in ways that make sense only if light's energy comes in discrete, indivisible packets. Not a smooth, continuous flow, but individual lumps of energy that arrive one at a time, each carrying a specific, measurable amount. Understanding what those packets are, what they really are at the deepest level, requires stepping beyond classical physics entirely. It requires quantum mechanics. And what quantum mechanics reveals about light is something far more subtle and strange than either Newton's corpuscles or Maxwell's electromagnetic waves. Light is not a stream of tiny glowing balls, but it is also not simply a smooth, continuous ripple spreading through space. The truth doesn't fit neatly into any category our everyday experience prepares us for, and that is where we're headed next. By the end of the 1800s, physics seemed nearly complete. Maxwell's equations described light as an electromagnetic wave. The wave theory explained reflection, refraction, interference, diffraction, and polarization with breathtaking precision. Electricity, magnetism, and optics had been unified into a single, elegant framework. Newton's mechanics described the motion of everything from falling apples to orbiting planets. Thermodynamics governed heat and energy. Many physicists genuinely believed the major work was done. There were a few small, loose ends to tidy up, but the fundamental picture of reality seemed settled. One of those small, loose ends was the problem of how hot objects glow. You've seen this countless times. Heat a piece of iron and it begins to glow. First a dull red, then a brighter orange, then yellow, then, if you can get it hot enough, a brilliant white. The color of the glow depends on the temperature. Cooler objects glow red. Hotter objects glow white or even blue-white. This is called thermal radiation, and every object with a temperature above absolute zero emits it. Your own body radiates infrared light continuously, which is why thermal cameras can see you in total darkness. The sun radiates across a broad range of wavelengths, peaking in the visible range, which is why sunlight appears white. The relationship between temperature and the color of emitted light was well established experimentally by the late 1800s. Physicists could measure exactly how much energy a hot object radiated at each wavelength. They could plot these measurements on a graph and produce a smooth curve showing the distribution of energy across the spectrum. The problem was that when they tried to explain this curve using classical wave theory, the calculations went catastrophically wrong. Classical physics predicted that as you move to shorter and shorter wavelengths, the energy radiated should increase without limit. Toward the ultraviolet end of the spectrum and beyond, the predicted energy should climb higher and higher, shooting off toward infinity. This meant that any hot object, even something as mundane as a warm oven, should be radiating infinite energy at ultraviolet wavelengths and beyond. Obviously, this doesn't happen. Ovens do not blast out lethal ultraviolet radiation. Hot iron glows red, not with infinitely intense invisible radiation. The prediction was absurd. Physicists called it the ultraviolet catastrophe, and it was not a minor technical issue. It was a fundamental failure of classical physics. The laws that governed waves, the laws that had worked so brilliantly for everything else, simply could not explain how hot objects radiate energy. In 1900, A German physicist named Max Planck found the solution. But it required him to make an assumption so radical, so deeply contrary to everything classical physics held sacred, that even Planck himself struggled to accept what it meant. Planck proposed that energy is not emitted or absorbed continuously, the way classical wave theory assumed. Instead, energy comes in tiny, discrete, indivisible packets. He called these packets quanta, from the Latin word for how much. Each quantum of energy is proportional to the frequency of the radiation. Higher frequency radiation carries larger quanta of energy. Lower frequency radiation carries smaller quanta. The mathematical relationship is simple and beautiful. The energy of a single quantum equals a constant multiplied by the frequency. That constant, now called Planck's constant, is extraordinarily small. It's roughly 6.63 times 10 to the negative 34 joule seconds. The smallness of this number is why we never notice quantization in everyday life. The individual packets of energy are so incredibly tiny that at human scales they blend together into what appears to be a smooth, continuous flow. It's like grains of sand on a beach. Each grain is an individual, discrete object. But there are so many of them, packed so closely together, that from a distance the beach looks perfectly smooth. Planck's assumption fixed the ultraviolet catastrophe beautifully. At short wavelengths, meaning high frequencies, each quantum carries a large amount of energy. It becomes increasingly difficult for the thermal motion of atoms to produce these high-energy quanta. The probability drops off sharply. So instead of the energy climbing toward infinity at short wavelengths, it peaks at a certain frequency determined by the temperature and then drops off. Planck's formula matched the experimental data perfectly. Every measurement, every curve, every data point. The agreement was exact. But Planck wasn't entirely comfortable with what he had done. He had introduced quantization as a mathematical trick, a calculational device that happened to give the right answer. He hoped someone would eventually derive his result from classical physics without needing the strange assumption of discrete energy packets. He didn't fully appreciate that he had just opened the door to an entirely new understanding of nature. It took Albert Einstein to walk through that door. In 1905, Einstein published a paper on a phenomenon called the photoelectric effect that took Planck's idea and pushed it further than Planck had ever intended. The photoelectric effect had been observed for years, and it had been quietly bothering physicists. When you shine light on certain metal surfaces, the light knocks electrons out of the metal. This itself wasn't surprising. Light carries energy, and that energy can dislodge electrons from atoms. What was surprising was how it happened. Classical wave theory made clear predictions about the photoelectric effect. In the wave picture, light is a smooth, continuous flow of energy. If you shine a dim light on a metal, the energy arrives slowly, so it should take time for enough energy to accumulate in one spot to kick out an electron. Increase the brightness, and you increase the energy flow, so the ejected electrons should fly out with more energy. And the frequency, the color, of the light shouldn't matter much. Energy is energy, regardless of the frequency of the wave delivering it. Brighter light means more energy, period. Every single one of these predictions was wrong. Experiments showed that electrons were ejected instantly, even in extremely dim light. There was no delay, no accumulation time. Even the faintest light, if it had the right frequency, knocked out electrons immediately. This made no sense if light were a continuous wave delivering energy gradually. Even more strangely, increasing the brightness of the light did not increase the energy of the ejected electrons. Brighter light produced more electrons, but each individual electron carried exactly the same energy, regardless of how bright the light was. This was completely baffling from the wave perspective. More energy arriving should mean more energetic electrons, but it didn't. And most puzzling of all, there was a sharp cut-off frequency, below which no electrons were ejected at all, no matter how bright the light was. You could shine an enormously powerful red light on a metal surface for hours, and not a single electron would come out. But switch to a dim ultraviolet light, a much fainter source at a higher frequency, and electrons popped out instantly. The frequency of the light, not its brightness, determined whether electrons were ejected. And above that cutoff frequency, the energy of each ejected electron depended only on the frequency of the light, not on its intensity. Einstein explained all of this in a single stroke of insight. He proposed that light doesn't just interact with matter in discrete quanta, as Planck had suggested. He proposed that light itself consists of discrete quanta, individual, indivisible packets of energy that he initially called light quanta, and which were later named photons. Each photon carries an amount of energy determined entirely by its frequency. One photon of blue light carries more energy than one photon of red light, because blue light has a higher frequency. One photon of ultraviolet carries even more. In Einstein's picture, the photoelectric effect becomes simple and elegant. A single photon hits a single electron. If the photon carries enough energy to overcome the forces holding the electron in the metal, the electron is ejected. If the photon doesn't carry enough energy, the electron stays put. It doesn't matter how many low-energy photons you throw at the surface. Each one interacts individually with an individual electron. 1,000 red photons, each carrying too little energy, cannot pool their energy together to eject a single electron. It's all or nothing. One photon, one interaction, one decision. Enough energy or not enough energy. This explained everything. The instant ejection, because a single photon delivers all its energy at once, no accumulation needed. The independence of electron energy from light intensity, because brighter light just means more photons, each still carrying the same individual energy. The sharp frequency cutoff, because below a certain frequency, each photon simply doesn't have enough energy to do the job. Einstein's explanation was complete, elegant, and correct. But it raised an enormous question. If light is made of individual photons, discrete packets of energy, then what happened to waves? What happened to Maxwell's beautiful electromagnetic wave theory? The interference patterns, the diffraction, the polarization, all the phenomena that proved beyond any doubt that light is a wave. Were those experiments wrong? Was Maxwell wrong? No, Maxwell was not wrong. The wave experiments were not wrong. And this is where the story of light becomes truly strange. Light really does produce interference patterns. It really does diffract through narrow openings. It really does exhibit all the behaviors of a wave. And light really does knock out electrons one at a time. It really does deliver energy in discrete, indivisible packets. It really does behave like a collection of individual particles. Both descriptions are correct, and neither, by itself, is the whole truth. To see this at its most vivid, consider a version of Thomas Young's double-slit experiment, but with the intensity of the light turned down so low that only one photon passes through the apparatus at a time. You set up the same experiment. A light source, a barrier with two narrow slits, and a detector screen on the other side. But instead of a bright beam, you use an extremely faint source that emits photons one by one. Each photon passes through the apparatus alone. There's no other photon to interfere with. It's a single, solitary quantum of light, traveling through the setup all by itself. When a single photon arrives at the detector screen, it hits at a single, definite point, not spread out like a wave, a single, localized impact, like a particle hitting a wall. You can see the individual detection events as tiny dots, appearing one at a time on the screen. If light were simply particles, tiny pellets flying through one slit or the other, you'd expect the dots to gradually accumulate into two clusters, one behind each slit. A simple pattern matching what you'd see if you threw tiny balls at two holes in a wall. But that's not what happens. As thousands and then millions of individual photon detections accumulate, one dot at a time. The pattern that emerges is an interference pattern. Bright bands where many photons arrive, dark bands where almost no photons arrive. The exact same pattern of alternating bright and dark stripes that Young saw with intense light over 200 years ago. The pattern that can only be produced by wave interference, by peaks adding together and peaks cancelling troughs. Each photon arrives as a single point, like a particle, but the collective pattern of millions of individual arrivals is shaped by wave interference. Each photon, individually, seems to know about both slits. It somehow passes through the apparatus in a way that reflects the wave nature of light, interfering with itself, exploring both paths simultaneously. And yet it arrives at a single, definite point, a particle-like detection event. This is not light being a wave sometimes and a particle other times. This is not light switching between two modes depending on the situation. This is something deeper. Light is a quantum object, and quantum objects do not fit into either the classical category of wave or the classical category of particle.
Those categories were invented by humans to describe the behavior of things at human scales, ocean waves and billiard balls, things we can see and touch. At the quantum level, nature doesn't respect those categories. So what is a photon, really? Here is the answer that modern physics gives, and it is both precise and deeply counterintuitive. A photon is not a tiny ball of light. It is not a small glowing pellet flying through space. It is not a miniature bullet emitted by a light source and caught by your eye. Those images, however natural they feel, are wrong. A photon is a quantum excitation of the electromagnetic field. Let's unpack that carefully, because it is the single most important statement in this entire discussion. The electromagnetic field is not something a photon travels through, like a fish swimming through water. The electromagnetic field is the thing the photon is made of. The field exists everywhere in space, at every point, in every direction. It's not a substance you can collect in a jar. It's a physical entity described by mathematics, a set of values assigned to every point in space and time that describes the electric and magnetic conditions at that point. This field is always there, even in the emptiest vacuum, even in the darkest void between galaxies. It's part of the fabric of reality. When the field is in its lowest energy state, its ground state, we call that the vacuum. No photons are present. The field is quiet, as calm as quantum mechanics allows it to be. A photon is what happens when you add one quantum of energy to this field, one discrete unit of excitation. The field, which was in its ground state, is now in an excited state with one photon present. Add another quantum of energy at the same frequency, and now there are two photons. Add 1,000,000 and there are 1,000,000 photons. Each photon is not a separate object placed on top of the field. Each photon is the field itself, vibrating, oscillating, carrying one unit of energy. Think of a guitar string. The string is always there, stretched between two posts. When nobody plucks it, it sits in its resting state. Now pluck it gently. The string vibrates. A wave travels along the string. That vibration is not a separate object sitting on the string. It is the string itself, displaced from its resting state, oscillating back and forth. The vibration and the string are not two different things. The vibration is a state of the string. A photon is like that vibration. The electromagnetic field is like the string. A photon is not something separate from the field. A photon is a state of the field. A specific, quantized, discrete excitation. One unit of vibration added to the electromagnetic field. Consider another way to see this. Imagine a perfectly still lake. The water is there whether or not any ripples are present. The lake doesn't come into existence when a wave appears and vanish when the wave dies out. The lake is always there. Now drop a pebble. A ripple spreads outward across the surface. That ripple is not a separate object placed on the lake.
It is the lake itself, disturbed from its resting state, carrying energy outward through the water. The ripple moves, but no water travels with it across the lake. What moves is the pattern of disturbance, the configuration of energy, not any substance. The electromagnetic field is like that lake. It exists everywhere, always, whether or not any photons are present. A photon is like one of those ripples, a disturbance carrying energy through the field. Remove the ripple and the lake remains. Remove the photon and the field remains. The field is the permanent entity. The photon is a temporary pattern of energy within it. This distinction matters enormously. It means photons are not objects traveling through the field the way a boat travels across a lake. Photons are the field itself in a state of excitation. They are patterns, not things. Configurations, not substances.
And this is why they can be created and destroyed so readily. Creating a photon means adding a quantum of energy to the field. Destroying a photon means the field surrendering that quantum to something else. The field itself is never created or destroyed, only its state of excitation changes. This is why the wave and particle descriptions are not contradictory. They are not two competing theories about two different substances. They are two complementary ways of describing the same underlying quantum field. The wave description captures how the field oscillates and propagates, how the excitation spreads through space, how it interferes and diffracts. The particle description captures the fact that the field's energy comes in discrete, countable units, that the field interacts with matter one quantum at a time, that detection events are localized. There are not two kinds of light, a wave kind and a particle kind. There is one kind of light, quantum light. Excitations of the electromagnetic field that propagate according to the field's wave equation and interact with matter in discrete energy units. The wave and the photon are the same thing described from different angles. This understanding didn't arrive all at once. It took decades of work by some of the most brilliant physicists of the 20th century. Through the 1920s and 30s, the new quantum mechanics was developed and refined, providing the mathematical framework for understanding how quantum objects behave. But quantum mechanics by itself wasn't enough to fully describe photons. You needed something more, a theory that combined quantum mechanics with special relativity and applied it specifically to the electromagnetic field. That theory is called quantum electrodynamics. Quantum electrodynamics is the full quantum theory of light and its interactions with matter. It was developed primarily in the late 1940s by three physicists working independently: Richard Feynman in the United States, Julian Schwinger, also in the United States, and Shin Ichiro Tomonaga in Japan. All three shared the Nobel Prize in 1965 for this work. The physicist Freeman Dyson showed that all three approaches, despite looking very different on the surface, were mathematically equivalent. They were three different languages describing the same physics. Quantum electrodynamics is, by some measures, the most successful theory in the entire history of science. It makes predictions that have been verified to extraordinary precision. One famous example is the magnetic moment of the electron, a quantity that describes how an electron interacts with a magnetic field. Quantum electrodynamics predicts this quantity to more than 10 decimal places. Experiments measure it to similar precision, and the two numbers agree, to more than 10 significant figures. That's like predicting the distance from New York to Los Angeles to within the width of a human hair. No other theory in any branch of science has ever achieved that level of agreement between prediction and measurement. In quantum electrodynamics, the electromagnetic field is treated as a quantum field. Photons are the quanta of this field. Every electromagnetic interaction, every instance of light being emitted, absorbed, reflected or scattered, is described as the creation, destruction or exchange of photons. Feynman developed an extraordinarily intuitive way of visualizing these interactions.
He drew simple diagrams, now called Feynman diagrams, that represent the fundamental processes of quantum electrodynamics pictorially. In these diagrams, straight lines represent charged particles, like electrons. Wavy lines represent photons. The points where lines meet, called vertices, represent moments of interaction. When two electrons approach each other and repel, what is physically happening? In quantum electrodynamics, one electron emits a photon, a quantum of the electromagnetic field, and the other electron absorbs it. The exchange of that photon transfers momentum between the two electrons, causing them to deflect away from each other. The electromagnetic force, the force that holds atoms together, the force that makes magnets stick to your refrigerator, the force that prevents your hand from passing through a table, all of it is mediated by the exchange of photons. Photons are the carriers of the electromagnetic force. This is remarkable. The same entity, the photon, the quantum excitation of the electromagnetic field, is both the thing we experience as light and the carrier of the force that governs almost every everyday interaction. The light from a lamp and the electric repulsion between two charged particles are both manifestations of the same quantum field doing different things. When you see a red apple, here is what is actually happening at the quantum level. Photons from a light source, carrying a range of energies corresponding to different frequencies, strike the surface of the apple. The atoms in the apple's surface absorb photons whose energy matches specific transitions in their electron configurations. The photons corresponding to most visible frequencies get absorbed, but photons with frequencies in the red part of the spectrum are not absorbed. Instead, the electrons in the surface re-emit photons at those red frequencies. These re-emitted photons travel outward, some of them entering your eye, where they are absorbed by photoreceptor cells in your retina. Each absorption event triggers a chemical chain reaction that sends an electrical signal to your brain. Your brain assembles millions of these individual photon detection events into the perception of a red apple sitting on a table. Every step in this process involves individual photons interacting with individual charged particles. Absorption is the annihilation of a photon, its energy transferred entirely to an electron. Emission is the creation of a photon from the energy released when an electron drops to a lower energy state. Seeing is the systematic detection and processing of countless individual photon events. And yet, through all of this, the wave description remains valid and useful. The photons traveling from the apple to your eye propagate as excitations of the electromagnetic field, exhibiting wavelength, frequency, polarization, and all the properties Maxwell described. The wave description and the photon description aren't in conflict. They're complementary aspects of the same quantum reality. This is what physicists mean when they say light exhibits wave-particle duality. But that phrase, wave-particle duality, can be deeply misleading if you take it too literally. It sounds like light is two things at once, simultaneously a wave and a particle, somehow switching between the two, or existing as both at the same time. That picture is wrong. Light is not a classical wave. Light is not a classical particle. Light is a quantum field excitation. It is something fundamentally new, something that has no analogue in everyday experience. It shares some features with classical waves and some features with classical particles, but it is neither. It is a quantum object, and quantum objects play by their own rules. The reason the phrase wave-particle duality persists is partly historical and partly pedagogical. It was a useful way to describe the shock physicists felt in the early 20th century when they realized light didn't fit into either classical category. It captures the genuine strangeness of quantum behavior. But it can also create the false impression that light is somehow confused about what it is, or that it switches back and forth between two identities. It doesn't. Light has one identity. It is a quantum excitation of the electromagnetic field. That identity has wave-like aspects and particle-like aspects. because those aspects are built into the quantum field itself. This brings us to a subtle but crucial point. The electromagnetic field is not optional or hypothetical. It is as real as any object you've ever touched. The field has energy. It has momentum. It exerts forces. It can be measured, manipulated, and described with extraordinary mathematical precision. The field exists at every point in space, whether or not photons are present. Even in a perfect vacuum, even in completely empty space with no matter or radiation of any kind, the electromagnetic field is there. In its ground state, the field fluctuates slightly due to the uncertainty principle. These vacuum fluctuations are not just theoretical, they produce measurable physical effects, such as the Casimir effect, where two uncharged metal plates placed very close together in a vacuum experience a tiny attractive force because of the quantum fluctuations of the electromagnetic field between them. This effect has been measured in laboratories and agrees with theoretical predictions. The electromagnetic field is not a mathematical convenience invented to make calculations easier. It is a physical entity, and photons are its quantized excitations. When you see light, you're not seeing objects flying through empty space. You're seeing the electromagnetic field itself in an excited state, vibrating, propagating, carrying energy and momentum across the universe. And quantum electrodynamics describes all of this with a precision unmatched anywhere else in science. Every interaction between light and matter, every photon absorbed by an atom, every photon emitted by a star, every photon exchanged between charged particles to produce the electromagnetic force, all of it falls under the umbrella of quantum electrodynamics. From the glow of a candle to the thermonuclear furnace inside a star, from the colors of a sunset to the signals in your optic nerve, quantum electrodynamics governs it all. But notice something interesting. We've established what a photon is, a quantum excitation of the electromagnetic field. We've established that the field is real, that photons carry energy in discrete amounts, that they interact with matter one at a time, and that the wave and particle descriptions are complementary aspects of the same quantum reality. This picture explains how light is emitted and absorbed. It explains the photoelectric effect. It explains interference patterns built up from individual photon impacts. But it hasn't yet explained some of light's strangest properties. A photon has no rest mass. How can something with no mass carry energy? How can it deliver a measurable push, a real transfer of momentum to a physical object? A photon always travels at exactly 300,000 kilometers per second in empty space. Never faster, never slower. Why? What prevents it from slowing down or speeding up? A massive particle like an electron can sit still, can accelerate, can move at any speed up to but not including the speed of light. A photon can do none of these things. It exists only in motion, only at one precise speed, from the instant it is created to the instant it is absorbed. And what happens when photons enter a material substance, like glass or water? Light appears to slow down in these materials. But if a photon must always travel at the speed of light, how can it slow down? These questions seem almost paradoxical. They pit our intuition against the mathematics, and answering them requires understanding a remarkable relationship between energy, mass, momentum, and the structure of space-time itself. That is where we're going next, into the heart of what makes light truly unlike anything else in the universe. We've established what light is, a quantum excitation of the electromagnetic field. Not a tiny glowing ball, not a smooth classical wave.
a discrete unit of energy carried by a quantum field that permeates all of space.
This picture is powerful and precise, but it immediately creates problems for our intuition. Because photons have no rest mass. Zero. None at all. And yet they carry energy. They carry momentum. They exert measurable physical pressure on everything they strike. They push things. They heat things. They sustain all life on Earth with the energy they deliver from the sun. How can something with no mass carry energy? How can something without any substance behind it deliver a physical push? And why does light always move at exactly the same speed? Never faster, never slower, in empty space. The answers to these questions take us into the heart of what makes light fundamentally different from everything else in the universe. And they begin with a closer look at what mass actually means. In everyday life, mass seems obvious. It's how heavy something is. You put an object on a scale and read the number. A bowling ball has more mass than a tennis ball. A truck has more mass than a bicycle. Mass is the stuff that things are made of. It's weight. It's substance. It's the resistance you feel when you try to push something heavy. Try pushing a car. It barely moves. Try pushing a shopping cart. It moves easily. The difference is mass. The car has more mass. It resists acceleration more strongly. This resistance to being accelerated, this stubbornness of heavy objects, is what physicists call inertia. Mass is a measure of inertia. The more mass an object has, the harder it is to change its velocity. The harder it is to speed it up, slow it down, or change its direction. But there is a specific and important concept here that most people never encounter. When physicists talk about the mass of a fundamental particle, they mean rest mass. This is the mass an object has when it is completely stationary, when it is not moving relative to the observer measuring it. Rest mass is an intrinsic property. It's built into the particle. An electron has a specific rest mass that never changes. A proton has a larger rest mass that also never changes. These rest masses are as fundamental to these particles as their electric charge. They are part of what defines an electron as an electron and a proton as a proton. A photon has a rest mass of exactly 0. This is not an approximation. It's not that photons have an incredibly small mass that we round down to 0 because it's too tiny to measure. It's exactly 0. Precisely 0. Fundamentally 0. The rest mass of a photon is 0 because of the deep mathematical structure of the electromagnetic field itself. In the language of quantum field theory, the electromagnetic field is what physicists call a gauge field. It has a specific kind of symmetry, called gauge symmetry, that governs its behavior. This symmetry is not optional. It's the foundational principle from which all of electromagnetism follows. Maxwell's equations, the behavior of electric and magnetic fields, the existence of photons, the nature of electromagnetic interactions, all of it flows from gauge symmetry. And gauge symmetry requires the photon to be massless. Adding a mass term to the photon would break this symmetry. It would destroy the mathematical consistency of the entire theory. It would lead to predictions that violate observed physical laws. The masslessness of the photon is not a coincidence or an accident. It is enforced by the deepest structural principles of the electromagnetic field. The photon must have 0 rest mass, or electromagnetism as we know it would not exist. Now, here is where things get interesting. In everyday life, mass and energy seem like separate things. Mass is stuff. Energy is what stuff does. A rock sitting on the ground has mass, but doesn't seem to have much energy. A bolt of lightning has tremendous energy, but doesn't seem to have much mass. We treat mass and energy as different categories. Einstein showed that this distinction is an illusion. In 1905, the same year he explained the photoelectric effect, Einstein published his theory of special relativity, and from that theory came the most famous equation in all of science. Energy equals mass times the speed of light squared. This equation tells you that mass and energy are not separate things. They are the same thing, measured in different units. Mass is a form of energy. Energy is a form of mass. They are interconvertible. You can turn mass into energy, which is what happens in nuclear reactions. You can turn energy into mass, which is what happens in particle accelerators when high-energy collisions create new particles. But the famous equation is actually a special case. It applies only to an object at rest, an object with zero momentum. The full relationship between energy, momentum, and mass in special relativity is more general. The total energy of a particle squared equals its rest mass energy squared plus its momentum energy squared. You can think of it as two separate contributions to the total energy. One contribution comes from the particle's rest mass. The other comes from its momentum, its motion through space. For a massive particle sitting still, the momentum is zero. The momentum contribution vanishes, and the total energy equals the rest mass energy. That's Einstein's famous equation. It tells you the energy locked up in the sheer existence of the particle's mass, even when the particle isn't moving at all. But for a photon, the situation is reversed. The rest mass is zero. The mass contribution vanishes completely, and the total energy comes entirely from the momentum. For a photon, energy equals momentum times the speed of light. Nothing else. A photon's energy is pure momentum energy. There is no mass energy at all. Every bit of energy a photon carries is in its motion, in its momentum, in its propagation through space. This is not a technicality. It's the key to understanding why light behaves the way it does. A photon is pure energy and pure momentum, with zero rest mass. It is motion without substance, propagation without inertia, a disturbance that moves through the electromagnetic field, carrying energy and momentum with it, without any massive object doing the moving. And this energy and momentum are real. They are measurable. They have physical consequences. Light exerts pressure. This is not a metaphor. When photons strike a surface, they transfer momentum to that surface. Each individual photon delivers a tiny push. One photon delivers an imperceptible push, but trillions upon trillions of photons, arriving continuously, can produce a measurable force. This force is called radiation pressure. The idea that light could exert pressure was predicted by Maxwell's electromagnetic theory in the 1870s. Maxwell's equations showed that electromagnetic waves carry momentum, and when they are absorbed or reflected by a surface, that momentum is transferred to the surface. In 1901, a Russian physicist named Pyotr Lebedev successfulully measured radiation pressure in his laboratory, confirming Maxwell's prediction. Around the same time, American physicists E.F. Nichols and G.F. Hull performed similar measurements. Light really does push things. In everyday life, you don't notice radiation pressure because it's extremely small. Sunlight falling on your outstretched hand exerts a pressure of only a few millionths of a pascal. That's far too small to feel with any human sense. The pressure of the air around you is billions of times stronger. But in space, where there is no air resistance, radiation pressure becomes significant over time. This is the principle behind solar sails. A solar sail is a large, lightweight, highly reflective sheet deployed in space. Sunlight hitting the sail transfers momentum to it, pushing it forward. The force is tiny, but in the frictionless vacuum of space, even a tiny continuous force adds up. Over weeks and months, a solar sail can accelerate a spacecraft to significant speeds without using any fuel at all. The energy comes entirely from sunlight, from photons bouncing off the reflective surface. In 2010, the Japanese space agency launched a spacecraft called Ikaros that successfully demonstrated solar sail propulsion. It unfurled a sail about 14 meters across and used the pressure of sunlight to adjust its trajectory in space. This was the first time radiation pressure from the sun was used as the primary propulsion for an interplanetary spacecraft. Light, massless light, pushed a physical object through space. Radiation pressure also explains why comet tails always point away from the sun. When a comet approaches the inner solar system, the sun's heat vaporizes ices on its surface, creating a cloud of gas and dust called the coma. The pressure of sunlight, along with the solar wind, pushes this material away from the sun, forming the comet's tail. The tail doesn't trail behind the comet like a banner behind a moving airplane. It points away from the sun, regardless of the comet's direction of travel. A comet moving away from the sun actually has its tail in front of it. Massless photons, carrying real momentum, sculpt comets visible to the naked eye. There's another beautiful demonstration of light's momentum. In 1923, Arthur Compton performed an experiment that provided direct evidence that photons carry momentum and behave like individual particles in collisions. Compton directed X-ray photons at a block of graphite. The photon energy was so far above the binding energy of the electrons inside the carbon atoms that the electrons behaved as though they were free. When a photon struck an electron, it bounced off with less energy and a longer wavelength, while the electron recoiled. The change in the photon's wavelength depended on the angle at which it bounced, exactly as you'd predict if you treated the collision as one between two objects, each with definite energy and momentum. This could not be explained by the classical wave theory. Only by treating the photon as a quantum carrying momentum equal to its energy divided by the speed of light. So the answer to how something with no mass can carry energy and momentum is this. Mass is not the only source of energy. Mass is one form of energy. Momentum is another. A photon has zero rest mass, so it has no mass energy, but it has momentum, and therefore it has energy. The full energy-momentum relation of special relativity accommodates both massive and massless entities. Massive particles get their energy from both mass and momentum. Photons get all of their energy from momentum alone. Both are valid, both are physical, both carry real, measurable energy. Now let's tackle the other great mystery. Why does light always travel at exactly the same speed in empty space? This speed, approximately 300,000 kilometers per second, is not merely the observed velocity of light, it is a structural constant of the universe itself. It appears in Maxwell's equations not as a measured input, but as an inevitable consequence of how electric and magnetic fields generate each other. When Maxwell derived the speed of his electromagnetic waves from the known strengths of electric and magnetic interactions, the speed that emerged was a fixed number. It didn't depend on the motion of the source, the motion of the observer, the intensity of the light, or the frequency. It was a single, universal constant. Einstein elevated this fact into a fundamental principle. The speed of light in vacuum is the same for all observers, regardless of their motion. This principle sounds simple, but it reshapes the geometry of the universe. It forces us to abandon the intuitive idea that time flows at the same rate for everyone. It forces us to accept that distances can contract and clocks can slow down, depending on how fast you're moving. The speed of light is not just a speed, it is a conversion factor between space and time. It tells you how much space is equivalent to how much time. It defines the geometry of space-time, the four-dimensional fabric in which all events occur. Everything with mass is locked into a relationship with this speed. As a massive object accelerates, its energy increases. Its effective inertia increases. The faster it moves, the harder it becomes to accelerate further. This isn't a matter of fuel or engine power, it's a property of space-time itself. The energy required to accelerate a massive object grows without limit as the object's speed approaches 300,000 kilometers per second. To actually reach the speed of light, you would need infinite energy. And infinite energy doesn't exist. Therefore, nothing with mass can ever reach the speed of light. Not with better engines, not with more fuel, not with any technology, however advanced. The barrier is not engineering, it's physics. It's the structure of reality itself. But photons have no rest mass. The constraint that applies to massive particles does not apply to them. In fact, the opposite is true. For a massless particle, the mathematics of special relativity doesn't just permit travel at the speed of light, it requires it. A massless particle cannot travel slower than the speed of light. It cannot travel faster. It must travel at exactly the speed of light, always, without exception. Here is why. Remember the energy-momentum relation. For a massless particle, the rest mass is zero. The total energy equals the momentum times the speed of light. Now imagine a massless particle at rest. Its momentum would be zero. Its energy would also be zero. A particle with zero energy and zero momentum is nothing. It doesn't exist. It has no physical reality. It can't be detected, can't interact, can't carry any information or influence of any kind. A massless particle at rest is an impossibility because rest would mean non-existence. Therefore, a massless particle must always be in motion. And the only speed consistent with having zero rest mass in the framework of special relativity is the speed of light. Not approximately, exactly. From the instant a photon is created to the instant it is absorbed, it travels at precisely 300,000 kilometers per second through empty space. It never accelerates from rest. It never decelerates to a stop. It springs into existence already moving at full speed, and it ceases to exist the moment it's absorbed. There is no in-between. This is profoundly different from the behavior of any massive object. A ball can sit still on a table. An electron can be nearly stationary in an atom. A planet can orbit slowly or quickly, depending on its distance from its star. Massive objects have freedom of speed. Photons do not. They are locked into a single velocity by the very structure of space-time and the fact that they carry no rest mass. Now let's connect the energy of a photon to something tangible, something you can see and feel. The energy of a single photon is determined by its frequency. Higher frequency means higher energy. Lower frequency means lower energy. Planck's relation tells you exactly how much energy a photon carries. Energy equals Planck's constant times frequency. Since frequency and wavelength are inversely related, this also means that shorter wavelength photons carry more energy and longer wavelength photons carry less. This single relationship explains why different parts of the electromagnetic spectrum interact with matter so differently, why some forms of light are harmless and others are lethal, why some pass through your body without effect and others tear apart molecules. Radio waves have very long wavelengths, measured in centimeters or meters, and correspondingly low frequencies. Each radio photon carries an extremely small amount of energy, so small that radio waves pass through your body constantly without causing any harm whatsoever. Right now, radio photons from dozens of broadcasting stations are passing through you. You don't feel them. You can't detect them without a radio receiver. Each individual photon carries so little energy that it cannot excite or disturb any molecule in your body. The photon arrives, interacts briefly with charged particles in your tissues, and the interaction is so weak that nothing happens. No chemical bonds are broken, no molecules are disrupted. The photon passes through or is absorbed without consequence. Visible light photons carry moderately more energy. Each photon of red light carries roughly 1.8 electron volts of energy. Each photon of blue light carries roughly 2.8 electron volts. This is enough energy to trigger chemical reactions in specialized molecules, which is exactly what happens in the photoreceptor cells of your retina. Light enters your eye, and individual photons are absorbed by molecules called rhodopsin and photopsins. The energy from a single photon is enough to change the shape of one of these molecules, which triggers an electrochemical signal that travels to your brain. Your ability to see is built on individual photon absorptions, one quantum of energy at a time. Ultraviolet photons carry more energy still, enough energy to break chemical bonds in certain molecules. When ultraviolet photons from the sun strike your skin, they can damage DNA molecules in your skin cells, breaking the molecular bonds that hold the genetic code together. If the damage is minor, cellular repair mechanisms can fix it. If the damage is extensive, it can lead to mutations that eventually cause skin cancer. This is why prolonged sun exposure is dangerous, not because of the intensity of the light, but because of the energy per photon. Each ultraviolet photon is an individual projectile carrying enough energy to snap a molecular bond. X-ray photons carry even more energy. They can penetrate soft tissue because the photons pass through without being absorbed, but denser structures like bone absorb X-ray photons more readily, which is why bones appear white on an X-ray image. The photons that make it through the body reach the detector. The photons that get absorbed by bone do not. The shadow of the bones is the image. Gamma-ray photons sit at the extreme high-energy end of the spectrum. Each gamma-ray photon carries enormous energy, enough to ionize atoms, shatter molecules, and damage biological tissue severely. Gamma rays are produced in nuclear reactions, in the decay of radioactive elements, and in some of the most violent astrophysical events in the cosmos. They are among the most dangerous forms of radiation precisely because each individual photon packs so much energy. And the key insight is this: all of these are the same phenomenon. Radio waves, visible light, gamma rays. They are all photons, all quantum excitations of the electromagnetic field, all massless, all traveling at the speed of light in vacuum. The only difference is frequency, and frequency determines energy. Planck's constant times frequency. One equation explains why radio waves are harmless, why visible light triggers vision, why ultraviolet causes sunburn, why X-rays penetrate flesh, and why gamma rays destroy living cells. The electromagnetic spectrum is not a collection of different things. It is one thing: photons, spanning an enormous range of energies. This perspective also reveals something subtle about the energy delivered by light in everyday situations. When you stand in bright sunlight, about 1,000 watts of power falls on every square meter of your skin. That sounds like a lot, and it is. But that power is delivered by an absolutely staggering number of individual photons. Each visible light photon carries only a few electron volts of energy.
To deliver 1,000 watts, you need roughly 10 to the 21st photons per second hitting each square meter. That's 1 billion trillion photons per second. The number is so large that the individual, discrete nature of the photon delivery is completely undetectable by your senses. You don't feel individual photons arriving one at a time. You feel a smooth, continuous flood of warmth and light. The quantum nature of light is hidden behind sheer numbers. It's like trying to hear individual raindrops in a thunderstorm. Each drop is separate, discrete, individual, but there are so many of them arriving so rapidly that you hear only a continuous roar. This is why classical physics worked so well for so long.
At human scales, with human senses, the quantum nature of light is invisible. The wave description captures all the behavior you can observe with ordinary instruments: interference, diffraction, polarization, refraction. All wave phenomena, all perfectly described by Maxwell's equations, all emerging from the collective behavior of unimaginably vast numbers of individual photons. The quantum nature of light reveals itself only when you look closely enough. When you build instruments sensitive enough to detect individual photons, when you study interactions between light and matter at the atomic scale, when you push the intensity so low that the discrete arrivals become visible, one dot at a time on a detector screen, that's when the smooth wave picture breaks down and the quantum reality shows through. Let's step back and appreciate the full picture we've built. Light is a quantum excitation of the electromagnetic field. Each photon carries energy equal to Planck's constant times its frequency. Each photon carries momentum equal to its energy divided by the speed of light. Each photon has zero rest mass. This zero rest mass is not a deficiency. It is a requirement enforced by the gauge symmetry of the electromagnetic field. Because a photon has no rest mass, it must travel at the speed of light. It cannot exist at rest. It cannot slow down. It cannot speed up. It exists only as motion, only as propagation, only as a traveling excitation of the field. The speed of light itself is not a property specific to light. It is a property of space-time. It is the speed at which all massless entities must travel. It is the maximum speed at which any causal influence can propagate through the universe. It is the conversion factor between space and time in the geometry of reality. Light happens to travel at this speed because light is massless. If gravitons exist, the hypothetical quanta of the gravitational field, they would also travel at this speed because they too would be massless. The speed of light would be more accurately called the speed of space-time, the universal speed limit embedded in the fabric of reality. And the energy that light carries, despite having no mass, is real and consequential. It warms the earth, it powers photosynthesis, it drives the weather, it enables vision, it causes sunburn, and at high enough energies, it destroys living tissue. It pushes solar sails through interplanetary space. It shapes the tails of comets. It transfers momentum in collisions with individual electrons. Mass is not required for energy. Mass is not required for momentum. Mass is not required for physical reality. A photon proves this with every interaction it participates in. Every time a photon warms your skin, every time a photon triggers a photoreceptor in your eye, every time a photon pushes a solar sail a fraction of a millimeter further through space, it demonstrates that the universe allows entities without mass to carry energy, exert forces, and shape the physical world. This is what makes light genuinely unlike anything else in our everyday experience. Everything you touch has mass. Everything you lift, push, throw, or catch has mass. Your entire intuition about how the physical world works is built on interactions with massive objects. Heavy things resist being pushed. Fast things hit hard because they have both mass and velocity. Energy requires something substantial to carry it. Light violates all of these intuitions. It has no mass. It cannot be held still. It doesn't resist being pushed because it doesn't exist unless it's already moving at full speed. And yet, it carries energy and momentum as real and measurable as anything a massive object carries. It is a form of existence that has no analogue in your tactile, everyday experience. It is pure field excitation, pure propagation, pure energy without substance. And yet you see it every day. You depend on it every moment. It fills every room you enter, warms every surface it touches, paints the world in colour, connects you visually to everything around you. The most exotic, most counterintuitive entity in fundamental physics is also the most familiar thing in your daily life. But we haven't yet explored what happens when this massless, speed-locked entity encounters something it can interact with. What happens when a photon meets matter? What happens when the electromagnetic field, propagating freely through empty space, runs into atoms, electrons, surfaces, and substances? Because light in a vacuum and light in a material behave very differently. Light bends when it enters glass. Light bounces off mirrors. Light is absorbed by dark surfaces and re-emitted by hot ones. Light curves around massive objects in deep space. All of these interactions, every instance of light being absorbed, emitted, reflected, scattered, refracted, or bent by gravity, are consequences of the electromagnetic field exchanging energy and momentum with matter and with the curvature of space-time itself. And that is what we're about to explore. In empty space, light travels freely. The electromagnetic field oscillates, electric and magnetic components generating each other in a seamless, self-sustaining dance, propagating forward at 300,000 kilometers per second without interruption, without resistance, without any loss of energy. A photon emitted by a distant star can travel for billions of years through the vacuum of space without changing its frequency, without losing momentum, without interacting with anything at all. In a perfect vacuum, light simply goes. Nothing slows it, nothing bends it, nothing absorbs it. The field propagates as if the universe were an empty stage. But the universe is not empty. Space is scattered with matter. Atoms, molecules, dust grains, planets, stars, galaxies. And when the electromagnetic field encounters matter, everything changes. Light bends. It bounces. It scatters. It gets absorbed and vanishes. It gets re-emitted as if created anew. Its apparent speed changes. Its direction changes. Its frequency can shift. All the strange and beautiful ways light behaves in the material world, from the colors of a sunset to the shimmer of a diamond, arise from one underlying process. The electromagnetic field exchanging energy and momentum with the charged particles that make up matter. Let's start with the most fundamental interaction: absorption. An atom consists of a nucleus surrounded by electrons. In quantum mechanics, these electrons do not orbit the nucleus like planets orbiting a star. They exist in specific quantum states, each with a definite energy. Think of these states as rungs on a ladder. An electron can stand on one rung or another, but it cannot stand between rungs. The energy levels are discrete, quantized, specific to each type of atom. A hydrogen atom has one set of energy levels. An oxygen atom has a different set. An iron atom has yet another. These energy levels are as unique to each element as fingerprints are to each person. When a photon encounters an atom, something very specific can happen. If the photon's energy exactly matches the energy gap between two of the atom's electron states, the atom can absorb the photon. The photon does not bounce off. It does not pass through. It ceases to exist. It vanishes entirely. Its energy is transferred completely to the atom, and one of the atom's electrons jumps from a lower energy state to a higher one. The electron has been excited. It has gained energy, and the photon that provided that energy is gone, destroyed.
it no longer exists in any form. This is not like a ball being caught by a mitt. A caught ball still exists in the mitt. An absorbed photon does not exist anywhere. It has been annihilated. Its energy lives on in the excited state of the atom, but the photon itself is gone. This is one of the most striking differences between photons and ordinary matter. You cannot destroy a tennis ball by catching it, but you can destroy a photon by absorbing it. Photons can be created and destroyed. They are not permanent. They are temporary excitations of the electromagnetic field, brought into existence when the field gains energy, and erased from existence when the field surrenders that energy to matter. Now, the reverse process. Emission. An excited atom doesn't stay excited forever. The electron in the higher energy state is unstable. After some time, typically a tiny fraction of a second, it drops back down to a lower energy state. And as it does, the energy difference is released as a new photon. A photon with a frequency corresponding exactly to the energy gap between the two states. The photon is not stored inside the atom waiting to be released. It doesn't exist at all until the moment of emission. It is created at the instant the electron transitions, conjured into existence from the energy the atom surrenders. This is the reverse of absorption. Absorption destroys a photon and excites an atom. Emission de-excites an atom and creates a photon. These two processes, absorption and emission, are the foundation of nearly all interactions between light and matter. Every color you see, every shadow, every reflection, every glow from a hot surface ultimately traces back to photons being absorbed and emitted by atoms and molecules. This is why hot objects glow. When you heat a substance, you are adding thermal energy to its atoms. The atoms vibrate more violently. Electrons get excited to higher energy states through collisions with neighboring atoms. And when those electrons drop back down, they emit photons. The hotter the object, the more energetic the collisions, the higher the energy states that get excited, and the higher the frequency of the emitted photons. A piece of iron at room temperature emits photons, but they are all in the infrared range. You can't see them, but you can feel them as radiant warmth if you hold your hand close. Heat the iron to about 500 degrees Celsius, and it begins to glow a dull red. The thermal energy is now high enough to excite atomic states that emit visible red photons. Heat it further to about 1000 degrees and it glows orange. The higher temperature means more energetic collisions and higher frequency photons. Push the temperature to 1500 degrees or more and it glows white, because now the iron is emitting photons across the entire visible spectrum: red, orange, yellow, green, blue, all blending together into white light. The sun glows white for precisely this reason. Its surface temperature is about 5500 degrees Celsius. At that temperature, atoms emit photons across the full visible range, producing the white sunlight we see every day. Now, let's talk about reflection, because it's not what you might intuitively think. When light bounces off a mirror or any shiny surface, it might seem like the photons are simply ricocheting, like billiard balls bouncing off a cushion. But that's not what happens at all. What actually occurs is a process of absorption and re-emission happening so rapidly and so coherently that the result looks like a simple bounce. When an electromagnetic wave strikes a metallic surface, the oscillating electric field of the incoming wave pushes and pulls on the free electrons in the metal. These electrons are not bound tightly to individual atoms. They're shared across the entire metallic structure,
forming what physicists call an electron sea. The incoming wave forces these free electrons to oscillate back and forth at the same frequency as the incoming light. And these oscillating electrons, these accelerating charges, radiate electromagnetic waves of their own. They emit new photons at the same frequency as the ones they absorbed, directed outward from the surface. The re-emitted wave has the same frequency, the same wavelength, and nearly the same energy as the incoming wave. It leaves the surface at an angle equal to the angle at which the incoming wave arrived. The result looks exactly like a simple reflection, but at the quantum level, it's a complete absorption and re-emission cycle happening in a coordinated, phase-locked manner across billions of electrons simultaneously. The incoming photons are destroyed, new photons are created. The reflected light is not the same light that arrived. It's new light, generated by the accelerating charges in the surface, carrying the same information as the original, but consisting of entirely different photons. Scattering is a related but distinct process. When photons interact with particles or molecules that are much smaller than the wavelength of the light, the photons are absorbed and re-emitted in random directions. The incoming photon is destroyed. A new photon of the same energy is created, flying off in a different direction. This is how light gets redirected without being absorbed permanently. One specific type of scattering explains one of the most familiar sights in everyday life: the blue sky. When sunlight enters the Earth's atmosphere, it encounters enormous numbers of nitrogen and oxygen molecules. These molecules are much smaller than the wavelengths of visible light. When a photon interacts with one of these molecules, it can be temporarily absorbed and quickly re-emitted in a random direction. But here is the crucial point. This process, called Rayleigh scattering, is not equally effective for all wavelengths. Shorter wavelength light, blue and violet, scatters far more strongly than longer wavelength light, red and orange. The probability of scattering is proportional to the inverse fourth power of the wavelength. This means that blue light, with a wavelength of about 450 nanometers, scatters roughly 4.5 times more than red light at about 650 nanometers. So, as sunlight passes through the atmosphere, blue photons are scattered in all directions far more efficiently than red photons. Red, orange, and yellow photons tend to pass straight through, continuing toward the ground in a relatively straight path. But blue photons are bounced around in every direction, scattered and rescattered by molecule after molecule. When you look at the sky away from the sun, the light reaching your eyes has been scattered toward you from all across the atmosphere. And that scattered light is predominantly blue, because blue scatters so much more efficiently. The sky appears blue because you are seeing sunlight that has been redirected toward your eyes by trillions of atmospheric molecules, and the redirected light is disproportionately blue. At sunset, the sun is near the horizon. Its light passes through a much thicker layer of atmosphere before reaching your eyes. So much blue light has been scattered away during this longer path that the remaining direct light is depleted of blue and enriched in red and orange. The sun appears red or orange at sunset because you are seeing the light that was not scattered away, the longer wavelength survivors of a much longer atmospheric journey. Now let's address something deeply counterintuitive. Light appears to slow down when it enters a material like glass or water. In a vacuum, light travels at 300,000 kilometers per second. In glass, it travels at roughly 200,000 kilometers per second. In water, roughly 225,000 kilometers per second. In diamond, only about 124,000 kilometers per second. This apparent slowing is what causes refraction, the bending of light as it passes from one material into another. But wait, we just established that photons must always travel at the speed of light. They cannot slow down. They have zero rest mass. The mathematics of special relativity demands that they move at exactly 300,000 kilometers per second. So how can light slow down in glass? The answer is that individual photons do not slow down. Between atoms, in the empty space inside matter, each photon travels at the full speed of light. But matter is full of atoms, and atoms are full of charged particles, electrons, and nuclei. When a photon enters a material, it encounters these charged particles almost immediately. The oscillating electric field of the incoming wave pushes and pulls on the electrons in each atom, forcing them to vibrate at the same frequency as the light. These vibrating electrons radiate their own tiny electromagnetic waves. The radiated waves overlap and interfere with the original wave, and the combined result is a wave that moves forward through the material at a slower effective speed. The light is not truly absorbed the way it would be by an opaque surface. The atoms never enter the discrete excited states we discussed earlier. Instead, the electrons are driven into forced oscillation, a continuous shaking rather than a quantum jump, and their response reshapes the wave as it passes through. The net effect is a delay. The electromagnetic field propagates at the speed of light in the empty gaps between atoms, but the continuous interaction with vibrating electrons across billions of atoms reshapes the wavefront, slowing its overall progress through the material. The cumulative effect of billions of these tiny delays across the thickness of the material is that the light as a whole takes longer to traverse the material than it would to cross the same distance through empty space. The effective speed, the average speed of the light's progress through the material, is lower than the speed of light in vacuum. But no individual photon ever travels below 300,000 kilometers per second. The slowing is a collective statistical effect arising from the interaction between the electromagnetic field and the charged particles in the material. An analogy might help. Imagine walking across a city at 5 kilometers per hour. Between intersections, you move at full speed, but every 30 meters you pause at a crosswalk for a few seconds, then resume your pace. If someone timed your entire crossing and divided distance by time, your average speed would be well below 5 kilometers per hour. All those brief pauses added up, even though you never actually walked slower between them. Light in a material is similar, though the mechanism is interaction rather than stopping. Each atom's electron cloud reshapes the passing wave slightly. The photon arrives at full speed, gets absorbed, a tiny delay occurs during the absorption and re-emission process, and then a new photon departs at full speed toward the next atom. The delays are incredibly brief, but there are billions of atoms across even a thin piece of glass. The cumulative effect of all those tiny pauses is significant. Light that crosses a 1 centimeter thickness of glass arrives about 17 trillionths of a second later than light crossing the same distance through empty space. That difference is undetectable by your senses, but it's enough to bend a beam of light at the boundary between air and glass, producing all the optical effects we associate with lenses, prisms, and the shimmering distortion you see above a hot road on a summer day. This effective slowing is what causes refraction. When a beam of light passes at an angle from air into glass, the part of the beam that enters the glass first slows down first, while the part still in air continues at full speed. This causes the beam to bend, like a line of marching soldiers turning a corner when one end of the line hits mud and slows, while the other end keeps marching on firm ground. The direction of the beam changes at the boundary between the two materials. Isaac Newton demonstrated this beautifully by passing white sunlight through a glass prism and showing that different colors bend by different amounts. Violet bends the most. Red bends the least. The white light separates into a rainbow of colors. Each color has a slightly different wavelength, and each wavelength interacts slightly differently with the atoms in the glass, experiencing slightly different effective delays and therefore bending by slightly different amounts. Now let's leave the realm of matter and talk about something even more remarkable. Light bends even in completely empty space, if that space is curved by gravity. Einstein's general theory of relativity, published in 1915, describes gravity not as a force pulling objects together, but as the curvature of space-time caused by the presence of mass and energy. Massive objects like stars and planets warp the geometry of space-time around them. Objects moving through this warped space-time follow curved paths, not because a force is pulling them, but because the space itself is curved. They're moving in straight lines through curved geometry, which looks like curved motion from the outside. Light follows these curves too. A photon passing near a massive object doesn't travel in a straight line. It follows the curved geometry of space-time, bending its path toward the massive object. The photon isn't being pulled by a force, it's moving through warped space. The photon still travels at the speed of light. It's still following the shortest possible path through space-time. But that shortest path, what physicists call a geodesic, is curved rather than straight, because space-time itself is curved. Einstein predicted this effect and calculated exactly how much a beam of starlight should bend as it passes close to the Sun. In 1919, the British astronomer Arthur Eddington organised 2 expeditions to observe a total solar eclipse. During the eclipse, when the moon blocked the Sun's blinding light, astronomers could photograph stars whose light passed very close to the Sun's edge on its way to Earth. If Einstein was right, those stars should appear slightly displaced from their normal positions, because the Sun's gravity would bend their light. The results confirmed Einstein's prediction. The stars were displaced by an amount consistent with what general relativity predicted. This was one of the most celebrated confirmations in the history of science. It showed that gravity bends light, not because photons have mass and are pulled by gravitational force, but because massive objects curve space-time, and light follows those curves. The experiment made headlines around the world and transformed Einstein from a respected physicist into a global celebrity. Today, we observe gravitational bending of light on far grander scales. Galaxy clusters, containing hundreds or thousands of galaxies bound together by gravity, contain so much mass that they visibly warp the space around them. Light from more distant galaxies behind the cluster gets bent and distorted as it passes through this warped region. The cluster acts as a gravitational lens, magnifying and distorting the images of background galaxies into arcs, rings, and multiple images. These gravitational lenses allow astronomers to study extremely distant galaxies that would otherwise be too faint to observe. The mass of the cluster amplifies the light, bending it toward us, acting as a natural telescope built from curved space-time. In some cases, the alignment is so precise that light from a distant galaxy is bent equally in all directions around the foreground mass, producing a near-perfect ring of light on the sky. These are called Einstein rings. They are among the most visually striking confirmations of general relativity ever observed. The distant galaxy, the foreground mass, and the observer all line up so closely that the bent light arrives from every direction around the lens simultaneously, forming a luminous halo. Each photon in that ring travelled at 300,000 kilometers per second the entire time. Each one followed a geodesic, the straightest possible path through curved space-time. The photons were not pulled or deflected by a force. They simply travelled through space that was warped by an enormous concentration of mass. The ring you see is the geometry of space-time made visible, etched in light. Let's step back now and see the complete picture. Every interaction between light and matter we've discussed, absorption, emission, reflection, scattering, refraction, gravitational bending, arises from the same underlying reality. Light is a quantum excitation of the electromagnetic field. Matter is made of charged particles. When the electromagnetic field encounters charged particles, it exchanges energy and momentum with them. That exchange is what we observe as absorption and emission. Coordinated exchanges across many particles produce the effects we call reflection and scattering. The cumulative effect of countless absorption and re-emission events produces what we call refraction. And when space-time itself is curved by mass, the electromagnetic field follows those curves, producing gravitational lensing. None of these behaviors require light to be a material object. None of them require a hidden medium. None of them require tiny glowing balls or classical pellets bouncing off surfaces. All of them follow naturally, inevitably, from the physics of a massless quantum field propagating through space-time and interacting with matter through the electromagnetic force. This is what makes light so profoundly strange and so fundamentally important. It is the most familiar thing in daily experience, and simultaneously one of the most alien. You see it every moment of your waking life. You depend on it for vision, for warmth, for food, for the very chemical reactions that keep your cells alive. Plants capture photons from the sun and use their energy to build sugars from carbon dioxide and water. Those sugars feed nearly every food chain on Earth. The energy driving virtually all life on this planet was carried here by massless quantum excitations of a field, traveling 150 million kilometers through empty space at 300,000 kilometers per second. Light is not a substance. It is not a thing in the way a rock or a molecule or even an electron is a thing. An electron can sit still. A rock can be held in your hand. Light cannot be stopped. It cannot be held. It cannot be slowed. It cannot exist at rest. The moment it stops, it ceases to exist. It is pure propagation, pure energy in transit, a temporary excitation of a quantum field that appears when energy is added and vanishes when energy is surrendered. It has no rest mass, yet it carries energy that warms planets and powers stars. It has no substance, yet it exerts pressure that sculpts comet tails and pushes spacecraft through the void. It has no size, yet it can spread across the entire observable universe, carrying information about events that happened billions of years ago to the instruments of astronomers studying those ancient lights tonight. It always moves at the same speed in empty space, not because nothing faster exists, but because that speed is woven into the geometry of space-time. It is the speed at which all massless entities must travel, the speed at which causality itself propagates through the universe. It interacts with matter one quantum at a time, one photon absorbed by one atom, exciting one electron. One photon emitted when one electron drops to a lower state. These individual quantum events, happening trillions upon trillions of times every second in every material object around you, produce everything you see. Color, brightness, shadow, transparency, opacity, reflection, refraction. All of it emerges from single photons interacting with single atoms, the cumulative effect of uncountable quantum events, producing the smooth, continuous, colorful world your brain assembles from the raw data of photon absorption. Understanding what light really is required overturning centuries of intuition. It required abandoning the idea that waves need a medium to travel through. It required accepting that energy comes in discrete, indivisible packets. It required reconciling wave behavior and particle behavior into a single quantum framework. It required recognizing that mass is not necessary for energy, that momentum does not require substance, that a field with no material presence can carry real physical influence across the cosmos. And the final understanding, the deepest one, is this. Light's strange behavior is not a collection of separate mysteries. It is not a list of disconnected oddities. Every counterintuitive property of light, its constant speed, its zero rest mass, its energy and momentum, its wave-like propagation, its particle-like interactions, its bending by gravity, its slowing in materials. All of it flows from a single underlying fact. Light is a quantum excitation of the electromagnetic field propagating through spacetime. That's not a metaphor. That is, as precisely as physics can state it, what light is. The electromagnetic field is everywhere. It is always present, even in the darkest void. And when it vibrates, when it oscillates, when energy is added to it in the precise, quantized amounts that the laws of quantum mechanics demand, we call those vibrations photons. Those photons carry energy and momentum through the universe at the speed that spacetime itself dictates. They interact with matter through the exchange of energy and momentum with charged particles. They follow the curvature of spacetime, sculpted by mass and energy. This is not a loose collection of facts about light. It is a unified, coherent, deeply tested understanding of one of the most fundamental phenomena in nature. An understanding built over 4 centuries by thousands of scientists, from Newton's prisms to Maxwell's equations to Einstein's photons to the breathtaking precision of quantum electrodynamics. Every experiment, every observation, every measurement confirms the same picture. Light is the electromagnetic field in motion, and the electromagnetic field in motion is light. You flick a switch, a room fills with light. It seems so simple. But behind that simplicity lies one of the deepest and most beautiful stories in all of science. A story about fields and quanta, about energy without mass, about a speed woven into the fabric of reality, about the quantum nature of existence itself. Next time you stand in sunlight, remember what is actually happening. Photons, massless quantum excitations of a field that permeates all of space, traveled 150 million kilometers from the surface of a star, crossed the vacuum of space at 300,000 kilometers per second, entered the atmosphere, scattered off trillions of molecules painting the sky blue, passed through the air, struck your skin, and transferred their energy and momentum to the atoms of your body. Each one was created in the nuclear furnace of the sun and destroyed at the surface of your skin. Each one existed only in transit, only in motion, only as a fleeting excitation of a quantum field. And there were trillions of them, every second, raining down from a star 93 million miles away. That is what light is, and that is why it behaves like nothing else in the universe.